This is Kaiser and Tintin, and
Welcome to our demo project.
Now, batteries are commonplace in today's society as they're easily accessible sources of energy storage. Known for being cheap and efficient, batteries are a monopoly of producing energy in today's society throughout the lives of many. However, how does this small metal cylinder work? What are its connections with our modern physical and chemical suppositions, as well as commonplace beliefs? Well, in order to explain this, we must first explore the history of our energy source, dating back to 1780s.
The invention of the battery as we know it is widely credited to Italian physicist Alessandro Volta for inventing the first voltaic pile, which is recognized as the first electric battery that was able to continuously provide an electric current to a circuit. However, this was not the first time the idea of electrical circuits providing power was brought forth. As early as the 1780s, a scientist named Luigi Galvani noticed that a frog's legs hanging on brass hooks would twitch when touched with a probe of some other type of metal. Galvani named this theory animal electricity. However, Volta, among few others, did not agree with Galvani's theory and instead thought it was due to an electric charge passing through metals with different properties. Volta found that he could produce an electric current by stacking layers of silver and zinc between layers of cloth soaked in salt water. He named his theory metallic electricity. Galvani believed that an animal's nervous system created animal electricity and was sent throughout the body, while Volta believed that an electric charge caused by two different metals could pass as electric current. So, who was correct?
It turns out that both theories were partially correct. Muscular contraction can occur due to electrical stimuli, as Galvani believed. However, there's no electricity that is unique to animals, a fact that Volta correctly deduced. Volta also correctly deduced that there was a flow of electrons between two dissimilar metals, brass and steel, which caused the frog legs to jolt.
What a great answer. I'd say that's a 4+.
Now, you may be wondering, how do modern batteries work? Well, you may have noticed, a battery contains a positive side and a negative side. And this refers to the two electrodes contained within the battery body, the anode and the cathode. Electrodes are conductors of electricity that makes contact with the non-metallic part of the circuit, such as the electrolyte, where the two electrodes are separated. More electrolytes later, but in simple terms, the anode is where the electrons leave the cell and the cathode is where the electrons are received. This happens through what is known as a reduction and oxidation reaction, also known as a redox reaction, where the anode is the oxidizing agent and the cathode is a reducing agent. The anode is negatively charged and loses electrons, or reduced in chemistry terms, while the positively charged cathode receives the electrons. But how is this all relevant to a battery cell being able to produce electricity? At the anode, anions, which are negatively charged ions, undergo oxidation through the circuit to the cathode. The cathode contains cations, which are positively charged and undergo reduction by gaining electrons to become a neutral atom. This respectively gives anode a positive charge as it loses electrons while the cathode gains a negative charge. The flow of electrons provide an electrical current that can be used to do work. Now, it should be noted that this also very much conveys the law of conservation of energy, as the chemical potential energy within the redox reaction process is transferred into electrical energy. This is, however, not an 100% efficient reaction process. Redox reactions are exothermic reactions, which meaning they are releasing more energy rather than consuming it in order to make the reaction happen. This means that energy is lost in the process in the form of heat and other means, causing the reaction not to be 100% efficient.
You may think that building a battery would be really difficult and complex to produce. However, that can be further from the truth. You can even build a battery at home. So with that being said, we're going to show you how to build a lemon battery. What you'll need for this battery is a lemon, a penny, and a zinc-coated nail.
First, roll the lemon and cut a slit into one side of the lemon. Next, place the penny into the slot you just cut. Finally, insert a nail into the other side of the battery. And there you go, you've made yourself a quick and easy lemon battery. If we hook up the battery to the multimeter, you can see the voltage of this battery is about 0.46 volts. With this battery, the lemon juice is the electrolyte. Lemon juice is very sour, which indicates that it is acidic. The lemon juice acts as a catalyst that allows electrons to flow from the anode to the cathode. In this case, the zinc-coated nail is the anode, and the copper-coated penny is the cathode.
Our lemon battery is very simple, so it should not be a surprise that it is not as powerful as your car or your phone battery. We can check the power using a multimeter, and we can check for watts because power is measured in watts. Remember that power is the change in energy over the change in time, or the rate of work done. And so our multimeter, we can't measure watts specifically, but we can measure two different things: voltage and amperage. Another equation we can use for power is power measured in watts is equivalent to voltage measured in volts multiplied by the amperage. Our lemon battery ran at 0.46 volts, and for reference, all AA and AAA batteries run at 1.5 volts, which is much more than our measly lemon battery. Now, you might be wondering why this AA battery is reading negative, and to answer that, we have to look back to Benjamin Franklin. Benjamin Franklin came up with the original convention for electricity flow. He believed that the positive charge terminal had a surplus of electrons that were carried over to the negative terminal. Conventional current flows from the positive terminal to the negative. However, we know that electrons do not flow from the positive terminal to the negative, as Tintin already has explained. So, this makes Benjamin Franklin's idea incorrect. The anode is negatively charged and has a surplus of electrons, which flow to the cathode in what is known as electron current. Electron current flows from the anode to the cathode. When we get a positive voltage on the multimeter, then we are measuring the electron flow from the negative terminal to the positive. And when we get a negative voltage on the multimeter, then we are measuring the conventional current flow from the positive terminal to the negative. Batteries die once all electrons from the anode stop flowing to the cathode. If we look at this multimeter, this AA battery has a voltage of 1.47 volts, which means that it has been used a bit as there are less free electrons in the anode available. In rechargeable batteries, which are also referred to as secondary cells, the electrochemical reaction that occurs in batteries can be reversible. Batteries work through an electrochemical reaction that transfers chemical energy into electricity. However, electricity from outside the cell can also be transferred into the cell, which will restore the anode's charge. The cathode, which normally receives electrons from the anode, now receives electrons from outside the cell. This makes the cathode side electrode negatively charged, while the anode side electrode has no free electrons. From there, electrons can flow in the opposite direction, from the cathode side to the anode side, and this will restore the battery's charge. Rechargeable batteries can be found in places such as phones or cars, with the most common type of rechargeable batteries being lithium-ion batteries. Due to the fact that batteries are rechargeable, they are technically considered renewable sources of energy, as the flow of electrons can be repeated to undergo another redox reaction.
With modern technology in today's society, we have been able to increase the efficiency of batteries to as high as 99%. Percent efficiency is measured as the amount of energy out over the amount of energy in, multiplied by 100. In today's society, batteries are the doors to many career opportunities such as electrical engineer, cell engineer, and much more. Electrical engineers work with the manufacturing of electrical equipments, including power generating equipment such as batteries. Similarly, cell engineers have the ability to design batteries of all types. They do this by utilizing the electrodes in a variety of designs in order to achieve maximum efficiency. You want as little chemical energy to be transferred to thermal while maximizing the amount of energy transferred into electrical energy by converting as much energy as possible per law of conservation of energy. Different batteries have different efficiencies depending on the type of metals and electrolytes used. For example, nickel-cadmium batteries use an alkaline electrolyte, potassium hydroxide, along with a nickel oxide hydroxide anode and a cadmium cathode. Nickel-cadmium batteries were once quite popular as they were one of the first widely rechargeable batteries. They provide a near constant terminal voltage during discharge and are lighter than its predecessors, lead-acid batteries. However, nickel-cadmium batteries are plagued with this issue where they would quickly lose capacity if they were not fully discharged before recharging. This means that you have to fully discharge nickel-cadmium batteries before recharging them. Nickel-cadmium batteries were once prevalent in portable electronic devices, but have been rendered obsolete by lithium-ion batteries, which have higher energy densities. Now, let's quickly talk about batteries' impact on the environment as a whole. Batteries can corrode due to the fact that an expected reaction happens within the battery body that causes hydrogen gas to build up, in turn causing a force of pressure to build up within the battery body that results in needing its release. This in turn can cause harmful chemicals to be released from the battery, to be released into soils, waters, and in turn causing contamination as a result. Batteries are not the most beneficial source of energy for the environment, but the use of batteries for energy storage allows for the production and use of renewable energy to be temporarily stopped
where renewable energy sources are undeniably intermittent in the production of energy. Overall, batteries are still quite beneficial in storing energy that needs to be readily accessible, but they're definitely more eco-friendly renewable energy sources that can be utilized in modern society.
We've talked about how batteries work and how to make more powerful and efficient batteries, but that still does not explain what forces specifically cause electrons to move in batteries. The fact is, the movement of electrons is credited toward the electromotive force, or EMF for short. This force is produced due to the redox reaction that takes place between the anions of the anode and cations of the cathode. The electromotive force can be defined as the characteristic of any energy source capable of driving electric charge around a circuit. This is more commonly known as voltage, which is the electrical force that allows free-moving electrons to move from one atom to another. Essentially, voltage allows for electrons to move from the anode to the cathode in the circuit.
Electromagnetic force, which is also one of the 4 fundamental forces we've been discussing in physics class, is also responsible for the movement of the electrons moving from the anode to the cathode. This is because the free electrons from the anode is attracted to the positive charge of the cathode, in turn causing the movement of electrons from the anode to the cathode in the first place. The strong nuclear force is also responsible for the underlying stability of elements by holding together protons and neutrons to form the atomic nuclei, keeping the battery stable. This also helps the battery continue doing what it's doing throughout its redox process for the electrons to be transferred. There is also gravitational force, which is what we learned in physics class that describes the attraction between any two objects. In this case, it's between the two electrodes, but it is so weak that it should be considered negligible. All in all, these forces come together to help produce the redox reaction and use the energy it produces to do work, as we talked about in physics, transitioning chemical potential energy to electrical energy per law of conservation of energy.
That being said, if there are forces acting upon electrons in batteries, then the electrons will be accelerating. So if you remember kinematics, your favorite unit, well, kinematics applies to batteries as well. If we know that the electrons are accelerating, therefore we can draw the AT, VT, and the DT graphs for electrons in a battery, and they will be shown right now. Within the circuits of a system, the electrons need energy in order to start moving from one electrode to another. Essentially quoting what Ms. Vlog has told us, let's say that you turned on your light. Electrons are always vibrating and moving, and when you apply a force to them by turning on the light, you increase the velocity of the electrons through acceleration. However, once the electrons are just flowing completely through the circuit, they will reach terminal velocity and stop accelerating. This acceleration is due to a property that surrounds us at all times, an electric field. An electric field is a physical, unseen field that surrounds electrically charged particles, in which an electric force is applied on another charge. The potential difference between the 2 points of electrodes causes electrons to accelerate from one electrode to another through the circuit until reaching a constant velocity. And as you know from kinematics, acceleration is calculated using the change in velocity over the change in time. These big ideas help everything tie into the mechanics of a battery, including the forces, kinematics, and energy of the power source. And that concludes our physics demo. Thank you for watching.
Neil? Hi. How are you? Batteries are a monopoly.
Wait, let's change it.
What the hell?
No, I'm changing it in millivolts.
Yo, Kaiser, did I just do like this?
Ah! What? Everybody!
I accidentally deleted one of your dog. You're yelling at your dog. All good.
Bro.
Bro, no, you can't even look at the screen.
Why is it still recording? Bro, no, bro, nah.
You can't even get the battery. Why?